Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over an introduction to thermochemistry where I'm going to go over the basics. So the first thing I want to go over, number one, what is thermochemistry? So thermochemistry is the study of energy transfer. And not only energy transfer, but it's energy transfer in the form of heat during chemical reactions and physical changes. So the terms that we're going to be dealing with are terms like energy, temperature, and heat. These are terms that are not interchangeable. They mean different things. So we got to be careful when we're using these terms. So this subject can be hard because our real life examples and definitions are not always scientifically accurate. So when we're talking about things with regard to energy transfer and do I feel hot or cold or whether energy is being absorbed or released, it can be a little difficult to kind of wrap your head around and see it from the perspective of the system. And so that's where our real life experiences and our ways of speaking kind of get in the way of that. So that's the first thing I want to talk about. So the next thing, we're going to get into these definitions and some other definitions and kind of define these terms. Okay, so let's define a few terms. So, what is energy? Energy, strictly speaking, is the ability to do work. And in this case, work has a technical definition. Work requires a displacement in position. In other words, something has to move. So, in order to do work, you have to have energy. And work is accomplished when something moves. So, if I push a box across the room, or if I pull a wagon across the street or something. If I'm doing that, if I'm making something move, then I am doing work, right? So that is what we mean by work. And so energy is the ability to do things, be able to move things, pull and push things, and things like that. So, what about this distinction between potential energy and kinetic energy? Potential energy is the energy that is stored energy. This is stored due to position and composition. For example, if I stretch a rubber band, the rubber band now has stored energy due to the position of the rubber band or the parts of the rubber band to itself. If I hold an object like this marker above the ground, the position of this marker with respect to the ground gives it a certain gravitational potential energy. So, depending on how far it is from the ground, it'll have more or less potential energy or gravitational potential energy. Uh, Also, another example of potential energy is chemical potential energy. That's the energy that's stored in bonds, right? So when you break bonds, you release that energy and then you can do work, right? So when you exercise in the gym and you're picking up weights, you're moving your muscles. That is then converting the stored energy that's stored into the chemical bonds of, say, the molecules like ATP or sugar that's being broken down. That energy is then released to help you lift weights or to do whatever you want to do. So kinetic energy, on the other hand, is energy due to motion. Anytime an object is in motion, it has kinetic energy. And so if I take the rubber band and I stretch it, now it has potential energy. If I let go, it's going to fly across the room. That potential energy is now converted into kinetic energy, the energy of motion. Okay, so things like that. So that's a few definitions. And so next we're going to get into the next topic, number 3, which is, the first law of thermodynamics. And here we go. Okay, what is the first law of thermodynamics? Well, the first law of thermodynamics is just like the first law of conservation of mass. So, if you remember, the first law of conservation of mass basically says that mass is neither created nor destroyed. It's transferred from one place to another, or it's rearranged or anything like that. But so the first law of thermodynamics says pretty much the same thing, but with respect to energy. Energy cannot be created nor destroyed. You can't make or destroy energy. So if something loses energy, then something else has to gain it. So if this object here is losing energy, then that energy is going into something else. And so the same thing vice versa. If this substance is losing energy, or whatever this object is, if that loses energy, then it's got to be picked up by something else. So this brings us to system versus surroundings. If you have a system that loses energy, then that's going to lose it to the surroundings. Everything else is the surroundings. Whatever you're focused on is the system, or whatever you define as the system is what you are focused on. And so if that system loses energy, then the surroundings is picking up that energy. If the surroundings is losing energy, then the system is picking up that energy. So energy in, energy out, right? So energy is not created or destroyed, it's just transferred from one place to another. The other thing is energy and mass are related to each other. So this is where Einstein's famous equation comes in, E equals mc squared. Energy is equal to the mass multiplied by the speed of light squared. C is speed of light, comes from the Latin celeritas, which is speed. So this equation tells us that energy and mass are related to each other. You can convert one into the other, right? So you can convert mass into energy, energy into mass. So if you can't create or destroy matter, then it stands to reason that you can't also you can't create or destroy energy. All right, so let me present a situation to you next. Okay, so here's the situation. Which would hurt more? A tablespoon of boiling water poured on you, or an entire pot of boiling water poured on you? And of course, everyone is going to say the pot of boiling water. And the reason for this, even though, of course, both the boiling teaspoon and the boiling pot are at the same temperature, boiling water at 100 degrees, you have more water molecules in the pot of water, and so therefore you have more heat that's stored in the boiling water. And so therefore, the more molecules you have that contain that heat can do more work on you by transferring that heat energy to you. And so let's talk more about this distinction between temperature and heat and how they're related. Okay, so let's talk about temperature versus heat. So number 4, um, temperature basically is a measurement of molecular motion. It's the measurement of the average speed of molecules, or the average kinetic energy of molecules, if you want to put it that way. So it deals only with the movement of molecules. Heat, on the other hand, is that energy that is stored and can be transferred due to the molecular movement. And so heat deals with the movement and the amount and type of particles. So this kind of gets us into what is called specific heat. So how much energy a substance can hold is going to depend on how much of that substance you have and the type of substance. Some substances are able to hold more energy than other substances. So, for example, water can hold more energy given a per gram, given a certain amount of that water versus a certain amount of aluminum. The same amount of aluminum can't hold as much of heat. So it's going to depend on a couple of things that I just mentioned. So it's going to depend on the amount of the substance you have and the type of molecules that you are dealing with. Okay, so let's talk a little bit more about this idea of being able to hold more or less heat. Okay, so for number 5, let's talk about which one has more heat. So we're talking about this difference between temperature and the amount of heat substance has. Here I have 2 pictures. Both are being measured by a thermometer, and they both read the same temperature. So both of these objects are at the same temperature. But then the question is, which one holds more heat? And you can see, obviously, this one here has more heat in it, because even though it's at the same temperature, it has a certain amount of heat tied to it. So bear with me, the pictures aren't drawn as equally as I wanted to, but assuming that these objects are the equal mass, equal size, um, so equal mass, but this one holds more energy in it. So why? Probably because of the type of substances it is. So this is made up of certain type of substance, certain molecules. Sorry about that. So because this is made up of a different substance, it's going to hold more energy even though it's at a different temperature. So this kind of illustrates this difference between temperature and heat. So even though they're at the same temperature, both objects are not holding the same amount of heat. This one has a greater capacity for holding heat than this one. So that is an illustration of this distinction between temperature and heat. So now let's talk about excuse me the idea of heat flow. Okay, so which way does heat flow for number 6? So here we have a hot object. If we're thinking about heat or temperature being related to motion and the motion of particles, then we would see, well, these particles are moving a lot faster than these particles. These are not moving as fast because they're colder, lower temperature. And so here, if you were to put these objects together, the heat would flow from the hot object to the cold object. Reason for this is because these are moving faster, and when they kind of bump into each other, when you put them together, they're going to be touching, and so these molecules are going to hit up against these molecules, and energy is going to be transferred from the hot to the cold. So the molecules here are going to transfer some of their energy here. So they're going to lose energy, meaning the temperature is going to go down. This is going to get cooler. And so these are going to pick up the energy. And so these are going to start to move faster. And therefore, the temperature is going to go up until they reach the same temperature, which means they're both going to then reach the same uh, speeds or motion. And so that is how heat flows. It always flows from hot to cold, areas of where it's hot to areas where it's cold until you reach an equilibrium. Okay. Now, what about uh, our speech? Okay, so let's talk about that. Okay, let's talk about how we speak. So I know it sounds strange when we're talking about heat moving from the hot to the cold object, but we always want to talk about heat moving in the direction of what is warming up, even though we know that the other thing is cooling down. So when we are talking about stuff in thermochemistry, we want to think about it in terms of the heat transferring from hot to cold, and we want to think of it differently for thermochemistry. So we want to think of it of moving in the direction of things warming up. So if you get this backwards, you're going to end up getting your plus and minus signs backwards too in the math. So it's really important to think of it in the right way when we're thinking of it in terms of thermochemistry and not the way we normally speak about things. So, for example, you don't want to say that the ice is cooling my drink down, right? We want to say that my drink, which is the warmer object, is heating up the ice. So we're thinking of it in terms of my drink, which has the heat is transferring to the ice and therefore heating the ice up. So we want to think of it in terms of the energy flowing in the direction from the hot object to the cold object, and we want to speak that way and think that way for thermochemistry, even though that's really not the way we speak or think in everyday life. But that's what makes thermochemistry a little bit hard and challenging when you're trying to think about things with respect to heat flow. Okay, so let's next talk about endothermic reactions or endothermic processes versus exothermic. Okay, welcome back. So let's talk about endothermic reactions or processes. So what does endothermic mean? That means that heat is being absorbed. So endo means into, therm is referring to heat. So heat is going into the object. So when the system, in this case, the reaction, absorbs heat, um, you are going to have this situation here where you have the object and heat is going into the object. So whatever our system is, whatever our perspective, our focus, that's our system. And that's in chemistry, it's the reaction. So when the reaction is occurring and it's endothermic, that means heat is being absorbed by the reaction. So in this case, what do you feel, right? So if I have a beaker and in the beaker there's a reaction going on, then what's going to happen is I'm going to feel cold. Why do I feel cold? It's because the system, the reaction that's happening in the solution in the beaker is absorbing heat. It's absorbing heat from the surroundings. I'm part of the surroundings. So it's going to absorb heat from me, and therefore I am going to feel cold, right? So that's because the reaction in the beaker is gaining heat from the surroundings, and I'm part of that, as well as my thermometer. Remember, with the thermometer, if I'm measuring the temperature of the substance in the beaker, that is part of the surroundings too. So it's going to absorb heat from the thermometer, and it's going to make the alcohol or the mercury in the thermometer lose energy, and it's going to contract, and that's what makes the line or the substance go down in the thermometer. So what about exothermic? Let's talk about exothermic now. Okay, what about exothermic? So before I go on, so here I have a little picture. Here I have my hand, and heat is flowing from my hand to the beaker or the object that I'm holding in my hand, right? So in this case, again, if it's an endothermic reaction, then if this is my system, my hand is part of the surroundings. And so if the system here is going to be absorbing heat, if it's endothermic, then it's going to be absorbing from my hand. And therefore, I feel cold because I'm losing heat from my body, right? So the same thing for exothermic, right? So if a reaction or process is exothermic, then that's going to be when a system or reaction releases heat. So releases heat, exo meaning out of, going out of. Exotherm, again, that's heat. So exothermic means heat is going out of the system. So here I have a picture here. Here's my object, here's my system, and heat is flowing out. So it's exothermic with respect to the system. And so in this case here, the question is, well, what do you feel when you are close to, or there's an exothermic process or reaction going on? And so what are you going to feel? That so this is when the system or the reaction releases heat. Heat is going out of the system. So in this case, heat, this is my system, heat is flowing out of the system and therefore being absorbed by my hand. Again, I am part of the surroundings. The system is releasing heat to the surroundings. My hand is part of that. My thermometer is part of that as well. So my hand and the thermometer are going to be picking up, absorbing that heat that's coming from the reaction, coming from the system, and that's going to make me feel hot. And that's going to make the thermometer go up. It's going to absorb the heat, and the thermometer goes up because the fluid inside the thermometer is expanding due to the heat that it's absorbing, right? So that's why you feel hot. Okay, so let me go over this. I'll go over some key points that I want to close on this with. Okay, so the question is, can I stick a thermometer inside a chemical bond? No, I can't do that, right? So remember, the heat that's being released or absorbed is related to the chemical bonds, right? So if I'm breaking bonds, that means that energy is being absorbed in order to break those bonds. If I am forming bonds, energy is being released when those bonds are formed. So I can't stick a thermometer into a chemical bond to measure the heat. So what I can do is I can stick a thermometer in the surroundings. And so when I have the thermometer in the surroundings, right? So if I have a beaker with a solution and I stick the thermometer in the solution where the reaction is taking place, then for an endothermic reaction, the chemicals or the system will be absorbing the energy. But the thermometer will show that the temperature is getting colder, right? So how can it be that something that's absorbing energy is getting colder? Well, you got to think about it from the perspective of the surroundings, right? The surroundings is losing that heat to the system, to the reaction, which is absorbing that energy from the surroundings. And so, because the thermometer is part of those surroundings, it's going to lose heat and then register a decrease in temperature, and things are going to get colder because the surroundings are getting colder, right? So if it's for an exothermic reaction, right, it's the opposite. The chemical reaction or the chemicals, which is the system, in this case, they will be losing energy to the surroundings, exothermic, right? So, but the thermometer will show it getting hotter, and that's because the thermometer, as part of the surroundings, is picking up that heat, is gaining that heat from the system, which is losing it, right? And so therefore the thermometer is going to register a rise in temperature because the surroundings is gaining more heat. So in the end, hot and cold depends on your perspective, yours or the reactions. And in chemistry, we're always looking at everything from the perspective of the reaction. So I hope that helps clarify everything. So next, I want to talk about temperature scales and how to convert between those different temperature scales like Kelvin and Celsius. So let's get into that. Okay, let's talk about temperature. So, what is temperature? Temperature is the average amount of energy in motion. So, this is measured with a thermometer. What do we mean by the average amount of energy in motion? This we're talking about the motion of the particles. So here we can see the particles, the length of the arrow represents how fast the particles are moving. Here we have slower moving particles. Here we have faster moving particles. So on this side, the average motion, the energy, the kinetic energy of the molecules here is going to be less than the average kinetic energy here. The molecules are moving a lot faster in this diagram here than they are here. So here we would expect that even though not every single molecule or atom is moving at exactly the same speed, it's the average we're looking at. So the average amount of motion or speed here is less than the average amount of motion or speed there. And so this is going to be related to temperature. So more motion or speed means that the object is going to be hotter, which means it's going to have a higher temperature. Less motion or speed of the particles is going to mean that it's going to be a colder object and have a lower temperature. Okay, so that's what we mean. That's what we mean by temperature. Temperature is a measurement of the average amount of energy, kinetic energy of the molecules that are moving, right? So, what about temperature units? Which unit should we use for temperature? So, we have those three scales that you may be familiar with. We have Fahrenheit. Fahrenheit is too annoying to use, so forget about it. So, we're not going to deal with Fahrenheit. Celsius, on the other hand, is much more convenient to use. It's usually used in science classes. It's easier to remember what the boiling point and freezing point of water is, right? 0 degrees Celsius for the freezing of water or the melting of ice, and 100 degrees Celsius for boiling water. That's a lot easier to remember than 32 degrees Fahrenheit and 212 degrees Fahrenheit. Um, so what about Kelvin? Kelvin is the absolute temperature scale. What do we mean by that? So Kelvin scale is the scale that measures all the way to zero. Zero is the absolute lowest temperature that you can get in the Kelvin scale, because the Kelvin scale is supposed to be measuring directly the motion of your particles. So it makes sense that zero means zero in the Kelvin scale. So if there's zero temperature in the Kelvin scale, then there must be zero motion, because we are tying the motion to the temperature. So no motion means no temperature. So the Kelvin scale is called your absolute temperature scale, because the lowest temperature you can get on the Kelvin scale is zero. And so this is going to be used for some calculations, some specific calculations like your ideal gas law calculations, which uses Kelvin, or when you use temperature in your other gas laws like Charles' law, you got to have your temperature in Kelvin, because the other temperature scales, Fahrenheit and Celsius, will give you negative values for things like pressure and volume, which doesn't make a whole lot of sense to have a negative volume and negative pressure. And you will get those if you use Fahrenheit and Celsius, because you can get negative temperatures with those. Okay, well, what about comparing the scales? So let's look at that. Okay, let's go over the different scales of temperature. So here we have my wonderful drawing. And here we have the three different thermometers. We have the Fahrenheit thermometer, Celsius, and Kelvin. And you can see that the markings, we're marking off the freezing point of water. And we have the boiling point of water as our two constants. And right away, you'll see that here we have 32 degrees Fahrenheit for the freezing of water, and we have 212 degrees Fahrenheit for the boiling of water. And for Celsius, it's 0 and 100. And for the Kelvin scale, it's 273 and 373. And so what you'll notice is right away that these markings for the Fahrenheit scale are closer together. They're smaller increments of degree, right? So our degrees Fahrenheit are smaller degrees, are smaller increments. If you look at the Celsius and the Kelvin scale, they have larger increments also. And I tried to show this in my picture, but it may not be perfect. The increments, the size of the increments of your Celsius scale and your Kelvin scale are the same size. So therefore, the number of increments between 0 and 100 is 100 here. And between Kelvin, we have 273 and 373. It's 100 increments there. So exactly the same number of increments between the Celsius and the Kelvin scale. And it's not the same. We have more increments for the Fahrenheit scale. So what this means is it's a lot easier to convert between your Celsius scale and your Kelvin scale, which I'll show in a moment. And so we can see that the difference between these scales, and this is, you have 180 divisions between 212 and 32. You can count that yourself. Subtract 32 from 212 and you get 180. So this part is divided into 180 increments. Both of these are divided into just 100. And so what are we going to notice? So notice how 1 degree of Fahrenheit is a smaller chunk than the degrees Celsius or the increment on the Kelvin scale. We don't say degrees Kelvin. We just say Kelvin, right? So we say 100 degrees 100 degrees Celsius, 212 degrees Fahrenheit, and 373 Kelvin. We don't say degrees. And there's a reason for that, but I'm not going to get into that right now. For these two scales here, to go from your Celsius scale and to the Kelvin, all you're doing is you're moving the 0 point down, right? So 0 here is going to end up down down here. So we're shifting the thermometer downwards until 0 matches with 0 on the Kelvin scale. And so you can see that the difference here is 0 and 273. So